Yeah, I'm the President Seong Kim from Yonsei University in Republic of Korea. I'm going to talk about the lithium polysulfide generation analysis on lithium-sulfur battery during repeated charging and discharging cycles. And here is my content. And in the previous presentation, the researcher presented the excellence of the lithium-ion battery, but despite the excellence of the conventional lithium-ion battery, there is still room for the further research to increase the performance of the lithium-ion battery. So So from these candidates, the lithium-sulfur battery has extremely high energy density, which 5 times higher than that of the lithium-ion batteries. And as you see in below, the global electric vehicle market is expected to experimentally substantial growth by 2030, and huge demand will inevitably result in the actual big consumption of the raw materials. So the sulfur, which is cheap and abundant compared to the lithium, is expected to have a major advantage as a material. But there is some two main limitations in the lithium-sulfur battery. First one is the fire hazard. The lithium-ion accumulate on the electric surface due to an irreversible reaction during the charging and discharging process, and it can cause the dendrite growth, as the student presented. So if the dendrite growth during the repeated charging and discharging, and here is the separator, the shortcut may occur, and this causes the fire. The second limitation is the low battery life cycle. In the lithium-sulfur battery, the reaction product between the sulfur and lithium has the high solubility, and it is dissolved into the electrolyte during the charging and discharging process. And this phenomenon is called the Shuttle effect. If the Shuttle effect occurs, it can reduce the battery life cycle by reducing electrode capacity and limiting the charge transfer of lithium ions. And this both important phenomena has the complex reaction and electrochemical kinetics, so it is hard to analyze the ion behavior over time and predict the inner state of the battery. Therefore, the elucidation of ion behavior mechanism and prediction of battery state is necessary. And here is the previous studies to elucidate the ion behavior in lithium-ion battery. In point of the experiment, they only provide a single morphological image after certain cycles, and they cannot provide the successive observation of the progressive changes in solid electrolyte interface. In the case of simulation, the existing modeling studies involve the simplifying assumption that may not capture or just capture some atomic scale essentially in repeated cycles. So there's the simplified assumption that they cannot compute the bone formation and have limitation on implement the repeated cycles, and they just propose the uniform electric field in the system. Yes, so I would like to develop the lithium-sulfur battery prediction protocol considering the entire battery life cycle and whole battery system. Yes, and in the previous study, I have already published the paper that introduced the computational protocol that provide a quantitative characterization and dynamic observation of dendrite growth. In this study, I implemented the atomic change distribution and voltage propagation. And by using this method, I would like to expand this study with the sulfur. Here is the ongoing project, and I would like to expand this study with sulfur, and sulfur materials has a different chemical reaction on the cathode side, so like the lithium-ion migration, and we have to implement the lithium-ion migration, lithium polysulfide generation, and Shuttle effect. And finally, we want to implement the entire lithium-sulfur battery prediction system. Yes, so for the elucidation of the ion behavior mechanism, Shuttle effect and dendrite growth phenomena should be precisely modeled. And for the precise modeling, the continuous cycles and voltage propagation and interactions between the cathode and anode should be implemented. And for these implementation, the charge reaction and charge transfer and electrochemical potential difference should be precisely modeled. For this modeling, we combine the three main methods in the molecular dynamic simulation. And the first method was the reactive force field that can model the bond breaking and formation. So we can use this method to implement the electrochemical reaction in the simulation. And second one is the EChem-DID method, which can calculate the voltage propagation and voltage equilibration. So we utilize this method to apply the repeated voltage on the electrode. And the third one is the charge equilibration method, and this method can calculate the charge distribution and charge transfer in the system. So by using this method, we can model the oxidation and reduction reaction in the in our system. So by utilizing our calculation protocol, we monitor the oxidation and reduction states of lithium according to the initial charge and discharging cycle. And during the equilibration step, due to the high reactivity inherent in the lithium metal and chemical reaction between the lithium and sulfur, lithium and DOL molecule during the initial SEI layer. Thanks. Without an electrochemical driving force. And during the charge cycle, the applied voltage reduced the oxidized lithium ion and deposit lithium metal atoms on the on the anode surface. And you can see the first discharge cycle in the upper plot. And during the discharge cycle, the large-scale oxidation of lithium metal atoms occurs, and the friction occurs on the anode side. And based on the charge distribution, the dendrite growth during the charging and discharge cycle can be observed. And because of the irreversible reaction during the repeated charging and discharge cycle, in the charge cycle, the oxidized lithium ion reduced on the anode lithium anode, and in the discharge cycle, the ion on the anode side oxidized to the electrolyte, and the electron consumption occurs. And to implement the shuttle effect, it is required to model the lithium ion migration during the discharging cycle. So although the lithium ion have not reached to the cathode interface, but it can confirm that they're still moving with the constant mobility. And as we derive the diffusion coefficient of the lithium ion, the value is fit with the previous studies. And also we check the octasulfur bond breaking during the repeated charging and discharging cycle. And as the concentration of the lithium increases, the bond with the octasulfur within the octasulfur breaks, and and the bond formulation occurs between the sulfur and lithium. And sulfur has undergone the bond breaking, so it can lower the potential energy, and the high concentration of lithium increase the interaction between the atoms, so it can increase the kinetic energy. And here is the conclusion. And by overcoming the limitation of existing computational studies, we can propose the simulation protocol that could analyze the ion behavior during the repeated charging and discharging cycle. So, and this protocol can reproduce the reaction between the electrolyte and electrode, and paving the way for comprehensive studies on how additives and salts influence the dendrite growth. And here is our future work. And I supposed to model the shuttle effect, but I just confirm the bond breaking of the molecule. So for the implementation of the shuttle effect, I would apply the reactive force field parameter within the system and and confirm the solubility of the lithium polysulfides during the charging and discharging cycle. And next step is just predicting, adjust my domain to the neural network system and predicting the lithium-sulfur battery simulation. Thank you for listening.
Thank you for educating us on the potential of the lithium polysulfide batteries. So the floor is open for some questions. Okay, you next.
I just have a quick question out of curiosity. So I'm assuming that these kind of dendrites occur in the cases of liquid electrolyte. Does anything like that happen also in the case of solid state lithium-ion batteries, if they're a thing?
You mean
where there's like a solid state electrolyte instead of a liquid one?
So as I know that that also occurs in the solid state battery, but it occurs more in the liquid state.
Okay, thank you.
Yeah, thanks for the talk. So my question would be, the system obviously used for the simulation, it's very simple one, far from what is actually being done on the actual lithium-sulfur technology, which I can understand is because make it simple for the simulation. So whatever was presented, already known challenges for lithium-sulfur batteries. I'm wondering how the simulation is gonna help the chemists and material scientists like me who are working in the lab. How is gonna help to find more challenges? Because if you want to simplify it, then how those information is gonna help us to improve the system?
You mean how the simulation can affect in the real system?
If you're gonna just do the simulation in such a simplified system, which is a bit too far from what the lithium-sulfur actually is, how does it gonna help?
What we want to do is to elucidate the ionic behavior on the interface between the electrode and electrolyte, because the mechanism in the solid electrolyte interface is really unclear. So we want to calculate the specific reactions and the behaviors in that point.
Thank you.